Hello everyone and welcome to this video on emission spectra. Now, in the lessons we looked at the different light given out by some elements, for example hydrogen, helium, etc., when we put them in a lamp. And what we saw is that each of our elements gives out sort of characteristic colours. Now these colours, like you can see on the screen, are referred to as the emission spectra of those particular elements. And they're kind of like a fingerprint. Each element has its own unique combination of colors or wavelengths which it gives out. So if you look at hydrogen, for example, there's some areas which are very similar to the next element, helium. However, there's some colors which are not common to the two of them. As you then go down to neon, sodium, for example, they all have their own characteristic emission spectra. Okay, so when we refer to an emission spectrum, we're really referring to the fact that when we heat up an element in its gas state, it will then emit only certain frequencies, or in other words, colors of light. And each one of these is called an emission spectrum. Now, this was a puzzle which confronted scientists for a very long time. However, thankfully, we have quantum physics, and quantum physics is the method by which we're able to explain what we observe, this idea of discrete energies being given out by each different element. Now, the way that we explain this in quantum physics is via something called atomic energy levels. Now, again, this may be something which is familiar to you. We have the idea that electrons exist in certain spaces, maybe shells, as you might call it in chemistry, and these shells surround that nucleus. So you can see on the screen here we have a blue nucleus, and I've got an electron which is in green there. I've deliberately enlarged it so that you can see it. Now, this idea of orbiting the nucleus hopefully is familiar. What you might not know is that quantum physics tells us that electrons can only occupy specific energy levels within the atom. And those are shown here via these black lines, n equal to 1, n equal to 2, n equal to 3. And we're going to discuss about how these energy levels then lead to the idea of an emission spectrum. So this is quantum physics that we've got to thank for this, and hopefully this is not too hard. Often when we think about quantum physics, we think it's going to be really, really difficult, but actually it's just a set of rules which we then apply and allow it to explain some things that we see. Okay, so as I just said, quantum physics says that we can have our electrons only in specific locations. So we're looking at the atom on the screen. The black rings tell us where the electrons can be. Each of these locations, each of these rings, is called an energy level. And we say that they are discrete. And what discrete means is kind of like steps, that there's only one particular position that we could be at any particular time. So my electron could be at n equal to 1, n equal to 2, n equal to 3, etc. Nowhere in between. In that way, those energy levels are discrete. Now, the electron you can see on the screen right now is in the lowest energy level, which is called the ground state, and it is closest to the nucleus. Now, our electrons could actually occupy any positions, okay, and as you know, when we're doing chemistry, we tend to fill up these shells or fill up these orbitals, you might call them. So it's possible for an electron to occupy either the n equal to 1 or the n equal to 2 or the n equal to 3 state, and so on. And there's actually more n equal to 4, 5, 6 states in our atoms. They're just not shown on the screen. Okay. Now, a key point about this is that if our electron has energy equal to 0, then that means it's got enough energy to leave the atom. And so in other words, the maximum energy that an electron can have when it's inside the atom is going to be just less than 0. If it has 0 joules of energy, that means it's just left the atom. It's free from the field which is keeping it within the atom. So the consequence of this is that the energies themselves are associated with negative energy values. Okay, I'm just setting you up for this because on the next screen you're going to see how we use these energies, and you're going to see a lot of negative energies. Really, the idea here is that the electrons have a negative energy, and that means they're stuck inside the atom. Don't worry about the consequences of that too much, just use the numbers as they're given. Okay, so you'll see these energy levels represented as circles, but they can also be represented as flat lines, as you can see here. Okay, so now we've gone from this circular view to a kind of flatter horizontal view. We're still using electrons here, and you can see there those numbers I talked about those negative numbers. Okay, so we've got three energy levels here: L3, which has minus 2.4, L2 minus 4.8, and then our final bottom one, which is the L1 state, so that'd be our ground state with minus 11.2. All of those energy levels times 10 to the minus 19 joules. Now, why has this got anything to do with spectra? Well, as you can see, our electrons can occupy different states. So, for example, my electron currently is in the level 3 state. However, it could drop down into the level 2 state. And if it were to do that, it would have to lose some energy. Its energy would have to become more negative. Okay. Now, the way that quantum physics explains this, it says, well, if you want to lose some energy, we're going to allow our electrons to lose energy by giving out a photon of light. Okay, and it's possible for it to give out a photon of light which allows it to drop from the L3 to the L2 level, or, for example, from the L3 to the L1 level. Could also go from the L2 to the L1 level, giving out another photon. So each time an electron drops down between two energy levels, it throws out a photon, and that photon carries some energy, and that energy is equal to the difference between the two energy levels. Okay, so we could take an example here. Let's look at the L3 to L2 transition. Okay, we can see that L3 has an energy of minus 2.4 times 10 to the minus 19. And then our L2 has minus 4.8. Well, if we wanted to drop down between the two, then we'd have to do a calculation. We take our first energy, take away the second energy, and we end up with an energy of 2.4 times 10 to the minus 19 joules. So what that means is that the photon, which is given out, that blue photon you can see on the screen, is carrying 2.4 times 10 to the minus 19 joules. Now, as we've learned before, if we have a photon, it carries energy HF, so I could actually calculate the frequency of that photon, and that would come up. We simply use our E equal to HF, rearrange, so we've got F equal to E over H, 2.4 times 10 to the minus 19, all divided by Planck's constant. That's our 6.63 times 10 to the minus 34. And we end up with a frequency of 3.62 times 10 to the 14. So, as we've said before, the different colors of light correspond to different frequencies. And so this would be a photon with a particular frequency. And we'd have to look up what that correlates to. It could correlate to something with invisible light. Equally, it could be something from the ultraviolet, gamma, infrared, any part of the electromagnetic spectrum. The point here is that different transitions are going to produce different frequencies dependent on the energy that they carry. So actually, you could try this one yourselves. Why don't you try calculating the energy and then the frequency of the photon which is released in that second transition from L3 to L1. Feel free to pause the video now and then just use the same approach as I've done for that blue one. Okay, if you're watching, then I'm assuming that you've at least had a try at this. Okay, we just do the same thing. We're starting at energy level 3, that's minus 2.4, and we're going down to 11.2. Okay, and so we're ending up with an energy difference there of 8.8 times 10 to the minus 19 joules. Notice there all I've done is found the difference basically between 11.2 and 2.4. Okay, to find our frequency, all we have to do is just do exactly the same process. That 8.8 times 10 to the minus 19 is going to get divided by our 6.63 times 10 to the minus 34, which is going to give us a higher frequency because it has a higher energy of 1.33 times 10 to the 15 hertz. Now, as I've said, there are multiple transitions here. However, this would explain the origin of two of the lines within the emission spectrum of this particular element. And these numbers here are made up, and so it's not a specific element we're looking at here. However, you could also calculate the energy between L2 and L1. And if we, for example, had an L4 there, we could calculate the frequencies according to three more lines. And the more energy levels we add, the more lines we can add, and the more we can complete our emission spectra. So that brings us to the end of this video. We've looked at ideas of spectra, energy levels, and then used them to explain those spectra as well. And that's a lot of physics. This is quantum physics, and it may be the first time you've used this, so really take some time to think about it. And if you've got any questions, please let me know. Thank you for watching.